All right, I think we started. So today we have a presenter who was in the Climate Cafe before, Yuri. He will introduce himself. And of course, we're in the Climate Cafe online, a weekly event with Sydney Staks from the municipality of Nijmegen. And today we're going to talk about the Perfect Sponge project. And well, actually, with no further ado, I will give the floor to Yuri to explain more.
Yes. Can you hear me right? Okay. Yes.
Yeah. Yeah, it's on a screen.
Okay. So yeah, from infiltration to evapotranspiration, from summer to winter and back. Subtitle. Right. So the reason for this project and for this presentation is basically combined challenges of heavier precipitation as well as heavier droughts and heat waves that I'm sure are not foreign to you. And basically, we are concentrating, of course, on temperate climate in Latvia, and we have a peculiar situation in summer season, and I believe this is quite true for most of Europe, is that the combined evaporation exceeds rainfall, and it's a bit, if you think about it, it's quite a strange situation. It's like a cognitive dissonance in a way, that because we know that most heavy rains and also flooding due to rainfall happens in summer, in warm period of the year. but we see, let's say, on this chart, that is basically there's more demand for there's more water lost or returned to atmosphere through evaporation than let's say than rainfall. And it gives like a very wide, but it's in the nature. It's in Latvia in general, right? Of course, it's different in the city, and the water balance is very different. We probably have much more runoff than transpiration because of hard surfaces. And this is, yeah, I mean, this is the challenge we are kind of working with. And what you see in the slide is, again, nothing new for this group in this room. Basically, one of the, let's say, promises of sustainable stormwater management or nature-based solution are multiple uses and multiple functions. So we no longer talk about just getting rid of the water, but about treating water in a holistic manner and getting as many benefits as we can in the process. That said, the notion or the term, I mean, the word itself, sustainable urban drainage systems, right? We drain something, we get water out. So it's quite clear, and we see it in many guidelines for SUDs, for nature-based solutions, for bioswales and rain gardens, is that these solutions have been historically designed by hydraulic engineers. So focused on hydraulic and getting the water away, having focus on infiltration, which is of course not optimal for the increasing challenges we had. So the focus of our research, and the reason we are in this room today, in such a big group, is that we try to find let's say some more optimal solutions for rain gardens. So we are looking at a combination of different design features as well as layering and plans that not only ensure effective infiltration but also maximize evapotranspiration. So this is the purpose of objective of this project that is also called Towards a Perfect Sponge. So we are yeah, and if I have to give another name for the project, it would be or objective. The ultimate objective, so to speak, is how to design a rain garden or a bioretention feature with zero discharge, basically. So how to have a perfectly circular water solution in bioretention. Right, and it's almost or officially it's even more than a year into the project. So we've done a lot of experiments, but first of all, we started with a literature review on previous studies, studying the role of evapotranspiration in bioretention, as well as factors that contribute to maximizing evapotranspiration. And what we have found out, surprise, that in order to get most water from bioretention features into the atmosphere, you have to have water, right? So water availability is the key. It's one factor, and another factor is the mechanism or a system to get this water out, and that's the plant, right? So combination of water availability and plant is actually the key to maximizing evapotranspiration. So you have to have the plant, and let's say if you are aiming at evapotranspiration, that should be, let's say, heavy drinking plant. And in the literature, it's been shown that more shrubby plants transpire more, but then you have to have water. So often a challenge in bioretention that's let's say suited for infiltration is that you infiltrate too fast and then the water is no longer. So traditionally many guidelines for plants in bioretention have stressed drought resilience of plant species, and of course it's another kind of design task to find some plants that could be resilient both in terms of water stress or dry conditions as well as saturated conditions. Right. So yeah, I'm not going to go too much into detail in this kind of slides. Basically, what you see is that we have tried combining different studies and comparing measured evapotranspiration rates. We see that there is a lot of variations. So it really depends on specific location, on specific design, and one of the things we are planning to do in future is to compare to the reference evapotranspiration to try to understand what is the real difference in those studies. But for now, let's say focusing on the experimental part, now that we have sort of learned that it's well, the combination of some plant system and water availability. So what combinations are effective, and how to really try them out in Latvian conditions. So what we did, starting from April this year, in a series of iterations, we have developed designs for bioretention metaphosms, which look like this barrel filled with layered soil, like drainage layer, and sand and soil substrates. we have Salix Integra plant, which is known to be quite resilient both for saturated and dry soil conditions, as well as quite heavy drinker and also looking quite nice. So here is the summary of the design parameters that we have varied. So we test for two factors. One is internal water storage, and another is the presence of the plant. And maybe coming a little back to this slide here, because I think I haven't discussed that. So the internal water storage is basically a raised drain. So this is this ensures storage of the water up to the up to the outfall point. And yeah, so in the literature it has shown that it increases water availability, and one of the study points for the study is to really test this, as well as to see how it impacts water availability, not only in the internal water storage per se, but also in the soil column above it. Right. So these are the design factors, and from June this year until September this year, end of June to end of September, for 3 months. So we've had 12 replicates of 4 different types tested on the university building's rooftop. So we try to replicate real-life conditions, meaning that, of course, the mesocosms, as we call them, received the rainfall, plus we have simulated the IP factor of 10 with a runoff coefficient of 0.7, meaning that basically each mesocosm received 7 times the amount of rainfall, right? 7 times the amount. Let's say, assuming that, I mean, rain gardens, like the typical ratio of area to the surrounding catchment area is 1 to 10. So this is how it worked. And we have been, let's say, collecting a lot of data. So we have been weighing the mesocosms, determining the weight of each barrel several times each week. So we've collected and registered all the data relevant for water balance, like added water, water removed through overflow, added weight, etc. We've had soil moisture and soil water potential sensors, as well as collected some data on nutrients and chemical parameters of the outflow, and of course the meteorological conditions to be able to estimate, estimate the reference evapotranspiration and relate, compare it to the actual evapotranspiration that we've estimated through mass balance method. You see the preliminary results here. So we had our hypothesis confirmed, that we see that there is statistical significance for the presence of plant, as well as statistical significance of for internal water storage. Something we have been surprised about, based on the literature. We had expected that the systems equipped with internal water storage would ensure between 30 and 50% higher evapotranspiration. Our difference was between 16 to 20%. So our hypothesis for why this difference is so small is that this has been a wet summer, and since the beginning of October we've conducted indoor experiments. I'm gonna talk about them in a minute. Yeah, and yeah, and of course, let's say we see that the difference between unpunted and punted system is huge, and it's very interesting that the design guidelines treat bioretention as it was plantless system, because basically it focuses on hydraulic parameters of the soil and infiltration. And you don't have this number here, but let's say in the study we also found that evapotranspiration accounts for between 30 to 40% of total water balance. So of 30 to 40% of all incoming water has been lost through evapotranspiration, having certain design considerations as well. Right. So as I have pointed out, we are now continuing the experiments indoors, and unexpectedly, and it's let's say a teaser for next Climate Cafe maybe, that we haven't seen expected difference in evapotranspiration between planted systems with internal water storage that you see here, and freely drained systems like this. So the difference has been very similar to what we have observed outdoors. And so we're still kind of, yeah, trying to understand why this difference is so small. And one of the points of this project is not only to study some specific combination of design parameters, because in this way we are able to test just two design variables, but also let's say the parameters for growing media depth and sand depth and things like that are set. So to study and to hypothesize about successful potential designs, we also do modeling in Hydros 1D environment for this for different designs. So at the moment we are trying to replicate the behavior of the mesocosms in the model, to replicate the observed results, and once it's done, we will change differences, assumptions, trying to change soil parameters, media layer depths, etc., to see whether we can improve it. Yeah, and in parallel, we are also working on digital twins, not just being the models, but also on data ingestion and data processing algorithms that would also, let's say, get some automated data, because something we are interested in is not only how to, well, one point in understanding whether the real life system we develop a prototype for is successful is to have field data. We can't have weighting glycimeters in every rain garden. It would be quite expensive to build, so we need some reliable method to evaluate evapotranspiration in the field, and that's why we are using soil moisture data as well as computer vision algorithms for estimating leaf area index and relating it to evapotranspiration. Yeah. Right. And this is a collective offer and effort, right? So you see, like, there are a lot of people involved, from Riga Technical University, Tartu University, Trent University, Hansa University of Applied Sciences, Groningen, and Red University. So yeah, as well as even school students who helped us with the Mazakosmos. So yeah, you know, we would like to. I'd like to use this opportunity to thank Janis, Ginta, Ines, Martins, Daniels, Peter, Elgars, Margit, Ulle, Alessandro, Giuseppe, Luca, Flores, Zander, and Martins. Right. So, and you, of course, for your attention. Thank you very much.
Nice. Thanks, Yuri. Very insightful, of course. And I think a lot in the call are more or less related to this research. But maybe some questions outside, because it will be, of course, one of the reasons why we present this would be great to get some feedback from others. Maybe Sietske or Sydney. Any questions to Yuri, or it's applicable for us?
Well, I was wondering, thank you for the presentation, by the way. Really nice research. I really like this, of course. I'm also fond of rain gardens, and I'm always wondering what's happening inside of the rain gardening itself. I'm usually busy with runoff areas, and we just treat the rain garden or bioswale like a storage area and an infiltration rate, and that's kind of it. However, the plants are very important for both infiltration and evaporation as well. So I really like that you are focusing on this, especially because if we have larger rain gardens of larger bioswales, then these evapotranspiration events do play a role in the water balances. But I'm glad that you find these results, of course, that you can influence it in some way, that you can see a difference. But I'm actually I'm anxious to know about those next steps you were talking about trying different soil compositions. And you now have chosen one plant type, and of course it's really interesting to know if you can play around with that as well. So I was wondering if well, you still have a lot of way to go, I think, for this research project, but does this give some prospects about the next steps, besides only changing the composition of the soil?
Yeah, well, it is my intuition at the moment that the soil type in the media type will not be that important. But of course it will be interesting to test in the in the digital twin, in the Hydros model, something. So I think well, something we've seen, and I mean these are, let's say, very preliminary results. Something we've seen from the indoor experiment is that the impact of soil moisture, or what we've seen is that the soil moisture is not that important for evapotranspiration, or in other words, the range of soil moisture at which evapotranspiration rate stays quite high, or quite optimal, is very broad, is very wide. And if let's say if the design objective is to really close the circle and to have the fully circular rain garden, something that I think we'll try and do next year, or in future, is so also even from the, let's say, from the theoretical limitations, seems like as let's say as as perfect as we can make this sponge, there still will be discharge, because like it's just much larger area that is drained to the rain garden. So for example, just a very simple calculation, let's say we well, and so there will be because this catchment factor of 10 or even larger will just make it impossible to evapotranspire all the water. But at the same time, so we've seen that this kind of internal water storage is working, and it allows storage of water. So something would be interesting to test is how can we use this stored water outside of the system. So there are, let's say, trees planted and other other vegetation surrounding not surrounding the bioretention. How this water could be used for irrigating other green surfaces. So basically, let's say stepping a bit outside of this narrow area of bioretention. That would be one thing. Another thing, of course, I mean, we've run a summer experiment. It would be very interesting to see how this functions, how the system functions year long. And what are design consideration, what are the design features that we would need to add to make it safe. Because, for example, if we well, the autumns tend to be very wet and very cold, so the transpiration. So just before the winter, the ground conditions are likely to be, let's say, very wet, and when the frost strikes, we have the freezing ground. So I mean, all this kind of function of plants, permeability, how then how the hydraulic parameters of soil change over the season would be quite interesting, of course.
Yeah, but still, it's still nice that in the hotter times, in the summer times, you can have these evaporation and make a more closed loop, because it's inherent that evapotranspiration doesn't occur that much when it's wetter. Well, it does when it's wetter, but when it's cooler.
Yeah.
And I also saw in your presentation that you guys want to find a correlation between leaf area. Did I notice that right?
Yeah.
Okay, but because that's really nice, interesting. Back on my question, because with the one plant, of course, you have different area, different transpiration rates from the plant itself. But also the area between the leaves, which creates the different micro situations for transpiration to occur. But I only saw it as that's something you still want to do. Is there still a prospect on finding that correlation only between leaves, or also maybe with the structure, or distances to the ground from the plant leaves, that kind of stuff?
Yeah, I think we're concentrating on the leaves now, but it's another rabbit hole to go down to.
Yeah.
So to see yeah, so and maybe not only the above the ground part, but also the underground part of the plants. What are the differences in the systems that let's say internal water storage? Well, it seems that it's just my guess that the systems with and it probably explains why we see comparable results even in indoors in drier conditions. That probably the systems that are freely drained the root growth is more active because the roots try to get more to the ground where water is available. So that also would be, I guess, quite interesting to study. But yeah.
All right, nice.
Absolutely. And others, if you want to fill in, of course, and help out, Yuri, you're more than welcome, I would say. Yeah. Maybe other aspects to brush on?
Well, I was
So-
wondering, I missed maybe some part about quite important, of course, the relations with the temperature settings that you measured in the in the laboratory conditions, because I saw the comparisons between the one with the plants and the ones with the drainage systems and all the different combinations. But I actually was expecting also some more data related to the temperature, or was it just like we just focused on these different conditions and set one temperature, or did I miss something?
Yeah, well, with the outdoor experiment,
Yeah,
has
of course.
been-
Then there is temperature changes. But in the indoors, the experiment, I was wondering if you set
Oh.
a certain condition, or did you try to simulate the outside conditions?
No, it's the temperature is basically stable there.
Yeah. Okay. Okay.
So
Yeah,
it's it's a very good question how to frame this experiment actually, because like
Mhm.
there's not many places, or should I say no place, or a few places where these conditions occur. Probably somewhere, I don't know, like south of Italy in September, where you have, let's say, a year-long, day-long average temperature of fluctuating around 22 degrees, and 1 month of dryness. Yeah, but I mean, I guess it's the point for the indoor experiment was to really see whether there are any kind of significant impact of varying.
Yeah, of course. Then you need
so-
to exclude a varying factor like temperature. But I was just wondering if that's what's the case. Yeah. All right.
Yeah, but it's very, and again, we have run now one drying cycle, so
Mhm.
basically fully saturating the mesocosms and letting them dry for some time. We originally expected first, let's say, decrease in evapotranspiration rate to occur after 2 weeks, based on other comparable studies that have studied, let's say, two-week period. And then we saw that the rate does not decrease. We waited for another week, and still the rate was basically the same. And then we waited another week, and then leaves on two of the plants starts turning yellow. So it was very like strange. The plants were going, and then they sort of stopped.
Suddenly.
It's like
Okay.
heavy. I mean, it's like
Yeah.
we have this inside joke, this Salix integra species. They're like heavy drinkers. It's like it's what heavy drinkers do. They drink
Yeah.
and then they fall.
And then
you
they
know?
fall. That's nice. Yeah. Yeah, that's a great metaphor. Yeah.
Yeah.
Okay, interesting. Yeah. Nice.
Yeah.
It's a very interesting project.
Yeah.
Yeah, we have a lot of fun. Yeah, so
Yeah.
and yeah, so we uh, where we will be working on a Horizon application for another project to maybe to expand this to drier conditions and maybe other types of nature-based solutions. And the working title for this project is Sponge Sucks.
All right.
Because of capillary suction. Maybe it's good to
Nice. Yeah. Yeah.
So if you want to be part of this project, let us know. You know.
Yeah, would be nice.
Yeah.
I'm sure
Yeah.
Sydney is
Well,
interesting. And then we
Yeah,
also,
well, I'm interesting, but there are a lot of parallels. We're having currently Thirsty Cities in Nijmegen, which is trying to get the data for these kind of things for trees, mostly not Salix integra, but other tree species. But the interesting part is the varying in the seasons, and especially that a lot of policymakers here, the green ones, think that more green is always better when it's really dry and when it's really hot, when we get these intense rainfall events, they will evaporate, and they think, oh yeah, we know something about it. It's really really nice, but actually the problem is that at high temperatures, the stomata really close, and evapotranspiration stops. So and we're now that's also something we know, but we don't know when that happens for every species, and it's actually really interesting to know what happens to the evapotranspiration in total, because not only as you notice, not only the plant itself above ground is important for the evapotranspiration, although it does matter. So there are some parallels to find, yeah, for sure.
Yeah.
absolutely. So we're able to put, so these experiments will probably go in the northern part of Italy, also in the Netherlands. So we can learn from this first project, I would say, and see
Yeah.
how it makes sense in other climates or regions. So it's going to be a nice follow-up. Yeah.
Yeah.
Any more additions or last questions before we look what we're going to do next week? No, I think everything is clear, right? Yeah. So what are we gonna do, Sydney, next week? Shall I tell everyone?
Well, you can tell better, I think, because there were some changes in the program. I'm not sure if the one from next week is still the same as we had. Is it still? Oh no, it's not one of Sparkles,
Yeah.
right? It's a water hub.
Yeah, exactly. So next week
Oh, yeah.
we travel from Riga, where we are now in Latvia, to a more warmer climate. Also without in this case without really severe winters. There will be Cape Town. So Christy's going to take us to the water hub, which is basically like a field lab with wetlands and other biofiltration. And of course that makes sense to really research for that region, mostly targeted on drought. They have, of course, day zero, so that's quite important. So Christy's going to take us to the water hub and also other challenges, of course, in South Africa, where we can learn from. So I would say come and listen next week again, and have a great evening. And thanks, of course, again for the great
Thank you
presentation.
very much
Jurijs.
for the
Yeah, thank
presentation
you.
on short notice. Really interesting. All right.
All right. Thanks a lot. Have a great
you.
evening.
Bye.
Bye-bye.
Um,
Thank you.